The strength of an acid is measured by its tendency to ionize, that is, to turn into ions. Let's look at the hydrohalic acids HX, where X represents a halogen. In water, most of the hydrohalic acids, except for HF, are completely ionized and exist as ions H plus and X minus. If a single arrow is used, as is the case here, the hydrohalic acids could be HCl, HBr, or HI. There are at least three factors that influence the ionization of HX: the polarity of the HX bond, the strength of the HX bond, and the stability of the conjugate base X minus. Let's start with point 1, the polarity of the HX bond. Recall that in a covalence bond, the sharing of electrons doesn't have to be equal. A bond is polar when there is a difference in the electronegativities of bonded atoms. All the halogen atoms are more electronegative than hydrogen, so they each have a larger share of the bonding electrons. Since the bonding electrons are closer to X, it bears a partial or slight negative charge, delta negative. That is, it is slightly richer in electron density. Hydrogen, being less able to attract shared electrons than the halogen, is poorer in electron density, so it has a partial or slight positive charge, delta positive. This means that H suffers from a relative shortage or lack of electron density. The more electronegative the halogen X, the closer the bonding electrons are to X, the more polar the bond. Now, a polar bond may break if there is a polar molecule nearby to encourage the bond to break. Water molecule is polar and its delta negative oxygen has lone pairs which are rich in electron density. The delta positive H in HX is attracted to one of water's electron-rich lone pairs, since oppositely charged regions, though small in magnitude, attract each other. Since H in HX has a smaller share of the bonding electrons, H might consider breaking off from its partner X and leave its electron behind. That is, H may want to leave as H plus and partner oxygen and water instead. The more polar the bond, the more H plus is ready to leave to combine with water to form H3O plus. That is, the more acidic HX is. Going by this reasoning, we would expect the most polar HF to be the strongest hydrohalic acid and the least polar HI to be the weakest hydrohalic acid. However, it turns out that this is not the case. The polarity of the HX bond is the least important factor in determining the acidity of HX. The other two factors are more important.